Okay, are you ready?
Okay.
Okay, let's have another BIMSA member seminar. This week we have the pleasure of having Professor Fengchun Lei, who is going to talk about a quick trip to knot theory and knot data analysis.
Okay. So, good afternoon. So first, I would like to thank the organizers to give me a chance to talk here. So today, I'm going to briefly introduce the knot theory and roughly explain how knot theory is used in data analysis. So my talk contains four parts. So first one, what is knot theory? So knot theory is an area of topology that studies knots and links. Now, a link is an embedding of the union of undisjoint circles in the space. In particular, we call one link a knot. So here are some examples and some examples of links. Now, a link naturally has n components, which are totally entangled in the space. And each component is in fact a node. The image of a node or link is also called a node or link. In the following, when we say a node, we usually mean a node or a link, except for some case specified. So two links are equivalent if there exists orientation preserving diffeomorphism, which take one to another. So two links are equivalent means implies they have the same number of components. Moreover, if one link can be deformed to another one in space by a sequence of deformation, such as stretching, or twisting, or bending continuously, and no cutting and gluing happens during the deformation. So equivalence may look quite different. See the picture here. A knot is usually denoted by its diagrams. A knot diagram is a project diagram of a knot on a plane in which only a finite number of double crossing points are allowed. And nearby each double crossing point, the undergoing arc is usually denoted by a solid line, so like the blue one. And the undergoing arc, usually by a broken one, here, like the red one. So a nature property of a knot K from its diagrams is as follows. Among all the diagrams of K, the least number of crossings is called the crossing number of knot K, and it's denoted by CK. So it is more clear. So the unknot has crossing number 0, and for the trefoid knot, so the crossing number is 3. and it is easy to check. So no cross number 1 and 2 nodes. There are 3 kinds of master moves on the diagrams. So they are defined in this picture. So for a straight line, so you can forward it in this way or in this way. So this is the first type of master moves. So for 2 parallel line arcs, so they can deform each other in this way. This is the second arm moves. So locally, for 3 arcs and 3 crossing like this, so we push 1 arc cross the crossing of the other 2 arcs from one side to the other side like this. This is the third move, third type of arm move. The arm moves are introduced by German mathematician Master in the 1930s. And he first proved the following theorem. So 2 nodes are equivalent if and only if their diagrams may be deformed into each other by a sequence of finite number of arm moves. So here is an example from the left side. So by a type 2 arm move, change to this one, and a small planar isotopy to this one, and further by a third type of arm move, change to this one, and then one move. So the left one and the right one so are equivalent. So Rademacher theorems is the basis of knot theory. It tells us how 2 diagrams of the same knot are related. However, it doesn't tell a bound of how many such moves are needed. The basic problem in the knot theory is the classification problem. Given any 2 knots, how do we determine whether they are equivalent? For example, how can we show the unknot, trivial knot, and trefoil knot are the same knot or not, or equivalent? Are they equivalent? You may try to use arm moves on one to see if it can be changed to another one. So this is the up one is trivial knot, unknot. The right lower one is the trefoil knot. However, you may find that you cannot succeed after trying many times. But this doesn't imply they are not equivalent. Maybe the time you tried is not enough long, or you might try in a wrong way. So in fact, as we will see later, there are really different knots, unequivalent knots. So no matter how long you try, how you try, you can never succeed. So a property P of a knot is called an invariant property, or simply invariant, if all the links equivalent to K also have the property P. For example, for an unlink L, it is clear that the number, the components of the link, the number of the components of the link N and the cross number are the invariants. Thus, for any N link with N is greater than 1, it is not equivalent to any node, a single component. So if the cross number of two links are not equal, they are not equivalent. But however, if two links have the same cross number, it doesn't imply they are equivalent. So the main task of knot theory is to find the invariants which have the strong abilities to detect the different knots. And the invariants also are easier to calculate. So here is a knot list given by cross numbers from 0 to 9. So since they have, so different group have different cross numbers, so they are not equivalent. So next we come to the part 2. We so far we have not yet proved which nodes are non-trivial. A knot diagram is tricolorable if each connected arc in the knot diagram can be colored by one of the three colors. For example, say red color, green color, and blue color, and satisfy the following two conditions. At least two colors are used, and at any crossing of the diagram, either the only one color appears, or all the three colors are used. So if every diagram of a knot K is tricolorable, we say K is tricolorable. So this tricolorability is well defined due to the following theorem, which say the tricolorability is not invariant. So this can be checked. The three advanced move. So the trefoil knot is tricolorable. So for the under the left one, so we can it colored satisfy our rules. But the unknot is a single component, so only one arc can be used. So it is not tricolorable. So by our theorem, they are not equivalent. And next example, so for the trivial two link, two components like this. So they are tricolorable. So since no crossing here, so only one is enough. So at least two colors used here, one red and another is blue. For the half link, so we can see from the picture, so each component have only one arc. So whenever you color them, so they cannot, you can use at most two colors. So it's not tricolorable. So by the theorem, so the trivial two link are not equivalent to the half link. So next we see the chirality. So given a diagram of node K, a crossing change in the diagram is shown in this picture. So in this picture, so the upgoing arc changed to the lower going arc, or vice versa. So we call this change crossing change on a node diagram. So if we doing the crossing change on each crossing point in the diagram, we get a new diagram denoted by dm. We call it the mirror of D. The node determined by dm is called the mirror of the node K, and denoted by km. If a node and its image and its mirror are not equivalent, we say K is a chiral. Otherwise, K is chiral. So chiral, so we simply say, so right hand and left hand, so topologically not the same. So it's a result in our theory that the trefoil node is chiral. That means trefoil, the left trefoil is not equivalent to the right hand one. And figure 8 node is a chiral. So we can use such local move to change one to its image, to its mirror. As a curiosity, our chiral nodes are relatively rare. So among the first 35 prime nodes in the node table, less than 1 or third, a fourth are chiral. So is in some sense is much less. So now let's come to the third invariance, element invariance, the link number. A link L is called a oriented link. If each its components is assigned to an orientation. So for circle, so we have two orientations, so choose one. For that oriented to link and a crossing of the two components, so with assign +1 or -1, so according to if the for example the red one change to the blue one change to red one in anti-clockwise way. So we assign the +1, and in the other case we assign it minus. We call the sign. We call the +1 or -1 the sign of the crossing, and denoted by the sign of C, the crossing. So the link number of the link, two components link, is defined by this formula. So it's the half sum of all the sign between and the crossing points between L1 and L2. So for the oriented link J, the link number is defined to be the sum of all the link number between different components. So here's the theorem. So the link number is an invariant of oriented link. So we can use this invariant to distinguish. So these two half link, so with different orientation. So the left one has link number 1, and the right one has link number -1. So they have different invariant. So they are not equivalent. Next, so we go to the part, not data analysis. We will explain how not theory is applied in data analysis. So the application of knot theory in molecular biology and the chemistry, so in widely ways. So it is known that a molecule of DNA has a double helix structure with two intervening linear strings and not linear axis, like this. So here is a knot, and the two sides are a link. Usually a link. So a piece of DNA can break and recombine, and finally, the structure of DNA may be changed physically. So the process is very similar to what happens in the knot theory, like this. So knot theory has been applied in molecular biology and chemistry widely. For example, we can use various knot invariants, chirality, link number in the biology. So here is some example. The molecule of laminin is chiral. So this is the left one, and this is the right one. Chiral means they are not equivalent. The left one has a harsh lemon scent, but the right hand one has a more pleasing orange scent. The molecule of drug thalidomide is chiral. It was once given to the pregnant woman to avoid morning sickness. Besides the reducing of sickness, it also caused birth defects. Later, it was found that the L1 was making the mother feeling better, but the D1, the right one, was causing the damage of the fetus. So if a drug is known to be chiral, the farm company need to try best to make the preferred form to minimize the side effect and to maximize the positive effect. Usually it is costly since most methods of molecule synthesis doesn't distinguish between different chiralities. So in most of the cases, the wrong chirality produce negative effect on human bodies. Now we come to the structure of protein. So usually it has four kinds of structures. So the first one, primary structure, the linear amino acid sequence that makes up the polypeptide chain. So we usually call it the P chain of a protein. So the second structure is a stable structure formed by hydrogen bonds between some group of different amino acids, mainly including the alpha helix, like this one, and the beta sheet, like this one. So the other two structure will not be involved here, so we omitted the whole. A single amino acid consists of some groups linked to the central C alpha atom. So in the picture, so we have, so here the C alpha, here the C alpha one. And each P chain can be regarded as a linear graph whose vertex set consists of all such C alpha atoms. And the edge set consists of all the edges connecting adjacent C alpha atoms. So here's a picture of the linear graph. The vertex are all the C alpha atoms, and the edge are connecting adjacent vertex. So all the P chains, so as an arc in the space, can be noted, and also can be linked each other. So for arc, so we can also do the note operation. It can be noted very complicated. And locally, so it can be folded in this way or in this way. Classical knot theory usually focus on the total properties of knots, regardless to the local information. But protein structures depends heavily on not only the total property, but also on the local information, locally how they folded. In knot theory, a knot can be deformed in a lot of ways. The figure can change. But they are regarded as the same one, before and after the deformations. So it is insensitive to local deformation. But the protein structure analysis is sensitive to local deformation. Such a deformation, even locally very small, may cause changes in protein structure, affecting the expression of the protein function. Knot theory usually studies the closed curves in space, while the P chains of proteins often contain one or more open curves. So we need to extend the research scope so that include the open curves and the local information. That's the difference. So the knot theory and the methods we used here. First, we extend the link number to simple curves, which may contain open curves. open curves. Let L1 and L2 be two disjoint open or closed curves in the space, which are parameterized as gamma 1 and gamma 2. The following integrals is called the Gauss-Link integral, with simply denoted by GL1 of the two curves, so defined in this way. We will also use the same notation as the link number, but here it is the Gauss-Link integrals. In fact, it is the average of the half of the algebraic sum of crossing signs between the two curves in any possible projective direction. So it characterizes the degree of the interlinking between the two curves. But why we use the same notation? Here is the reason. We have this. Here the theorem tell us why we use the same notation. So for two link J, Lj defined here, it's just the link number of J. So we use the same notation. So for open curves, L1 and L2, the Gauss linking integrals is a real number and continuously on the curve coordinates. So this is the basis we used in the application. So in the following, I introduce briefly the multi-scale Gauss link integral. And this can be used to detect the local and the total link of L. Here we have basically have four main steps. So the first one, segmentation. Divide the two curves in the space into finite segments, so Pn and Qm. So the segments are n by n. So this is to increase the sensitivity to the local deformation. Here's some examples of the segmentations. The second step is to calculate the segmentation matrix. So in the matrix, each item is Gauss linking integrals of the two segments. So this is n times m matrix. And we have a theorem, the ground sum of the segmentation matrix equals to the Gauss linking integrals. So that's the theorem. So we will use in our application. Here is some examples. The third step is to calculate the multi-scale segmentation matrix. So here, given a finite set of real number like this, the matrix of Gauss link integrals at the scale is defined in this way. So it's a n times m matrix. Each item is the item in the segment matrix which multiplied by a distance character function defined in this way. By use this matrix, so we know if the distance of two segments is not in the scale, and the corresponding Gauss-Link integrals of the two segments will be neglected. So here is a example. And we remark that this provides a way to capture the local interactions between segments in scale. So the Lincoln characteristics at the various scale can be quantitatively captured to detect the local structure. And the last step is obtain the multi-scale feature of the segmentations. So for a given scale, we define the localized scaled Gauss-Lincoln integrals at P1, at the arc P1 or Qj, so by this one or by this one. So this is just the sum of the I column in the MSM matrix. And this is the sum of the J row of the atoms in the matrix. And the MGLI provides a scaled visualization for each curve segment U in this way. So here are some remarks. So the global topological invariant properties are ultimately recovered when the scale is sufficiently large. The MGLI can naturally be applied, so not only to links, link noise, and also to many other objects, open, closed curves, including a single curve, and other segment objects. So now we come to the application. So we use the MGLI to analyze the protein flexibility. Proteins are flexible, usually. The flexibility is often measured by so-called B factors. Here, high B factors mean more atomic mobility, which shows flexible or conformation change paths. And the low B factors indicate the rigid regions, which with less atomic motion. So we consider the P chain or protein as an open polygon. So as before, so here we segment in this way. So here's the result comparison on the protein of 1V70 B factors. So here's a experimental result, and this is our result, and this is the usual method. The result from usual method. So we set the multi-scale this way, and not explain it in detail. And the visualization of protein 1V70 P factors obtained from experiments MGLI and GNM, so in this way. And this figure shows the periodization of protein B factors obtained from experiments or methods and GNM. And so here is a comparison of methods and other literature approach. So the comparison of B factor predictions between an MGLI method and the other literature approach on a benchmark data set or 364 proteins, so which show our methods is better than the usual one. And this is a comparison of the B factors predictions on the 3 additional benchmark database set between MGLI and other methods, so which show our methods are much better than the other one. So next we come to the closing remark. This is just the beginning of not data analysis. It contrasted to the previous qualitative and descriptive knot theory approach. So our method is quantitative and predictive stretch. It offers a tool in knot theory and opens an area in data analysis and knot learning. And this is also the first attempt to transform the invariance of knots into applicable quantities feature analysis, making it possible to apply more knot invariance. For example, not polynomial invariance following homology and homology, and as well as GLMY theory to many fields related to node data, and achieve more accurate and efficient data analysis. I think that's all. I'll stop here.
Okay, questions? You cannot have no questions. There you go.
I think maybe this is a little naive at this stage, but I was wondering if it would be possible to have some kind of stability results for your methods. So the idea you had, I think at the beginning, if I understood correctly, you have this segmentation of the strings or knots, and then you apply the Gauss integral to various subsections of this segmentation. And you were saying at the extremes, this gives you an answer you expect. So if you take the whole strand as a single element, then you get sort of the classical invariance. So by stability, I would mean that if you were to vary this number of segmentations somehow smoothly, then and you made a small change, then you would expect a small change in your outputs. You would have some kind of inequality. Do you think this is a plausible thing that result that could be attempted?
Can you repeat it, the last sentence?
So if maybe the way you set it up doesn't lend itself to this directly, but stability would be if you make a small change on the way you say the number of segmentations you have, would you expect a small change in the outputs, so a bounded change in the outputs? You have to say first what a sort of a continuous change is. Well, it sounds plausible, yeah.
I don't want to go over time, but let me ask you. I can't hold this. So this Gauss linking number, what kind of a function is that? So can you show the formula? So what are you averaging over? What kind of function is this?
So this one?
Not this one. That very definition of GLI. The integral formula.
Integral formula, yes.
Well, okay, yes. Then I ask you the question. Integral. The integral. GLI.
GLY here.
It's not here. It's previous.
Previous.
Here.
Okay.
So you are integrating over ds. You have two links. You parameterize them differently in the ambient space.
Yes.
These are local parameters on the links. Right? Okay, but then you're integrating, you're taking average over ds and dt. So, well, I know it looks like Laplacian. What is this measuring? Can you have self-intersection now?
No.
See?
Only different.
Then it's not cohomology, because cohomology gives you self-intersection. Well, if you take the circle and it intersects itself, can you have self-intersection?
You take a surface which is bounded, and then you see how many times the other circle intersects them. That is the definition of the gathering.
I see. So this you guys understand. Okay, I asked them. Any more questions? Let's thank the speaker again.
I'm sorry, over time.